So, thank you, Lucille, for inviting me here and giving me this opportunity to talk. So the commission was that I have to give a very elementary lecture to begin with. And I will try to do that, and then it's going to be more and more one. So the title is Geometric Recursion. So this is really joint work with Anton, Nicolas, and these two are both students of Bertrand Art, and Bertrand and Nicolas Anton invented topological recursion. And this geometric recursion is a kind of way to make geometric what topological recursion is. But I want to convince you that first that the setting in which we are working is very general. So the setting is the following. So we're considering the following to be given. So given the following in functor from the category of surfaces. And so in a second I will be specific about precisely which category of surfaces I mean. Right now just think of ordinary compact surfaces in free space. To the category of vector spaces. So, category of vector spaces, I will actually be looking at infinite dimensional vector spaces most of the time. Right now it doesn't matter so much. So this function I'm going to call it, say, V. And then, so V is going from some category of surfaces I'm going to call V for a moment. And then it goes to script V, which is the category of vector spaces. And it's given. Okay. So in particular, if I take sigma to be an object of B, so some surface, some compact oriented surface, then what I get is B of sigma, right? This is a vector. So the objective of this, so wish, or rather the construction, that we're going to discuss here, that we give you, is some kind of functorial natural assignment of an element inside the mapping class group invariant part of this vector space. So here gamma sigma, this is the mapping class group of sigma. So, the reason why the mapping class group acts on this vector space is because this category of surfaces, the morphisms of the category of the surfaces, is isotropy classes of diffeomorphisms. And so they form the mapping class group, and that's why they act on each of these vector spaces. And so I want to have a construction that gives me invariant vectors like this. So, if you look at this from this point of view here, very simple problem in some sense, and I want to claim that this is very, very, very general. I basically claim that everything we do, almost, in low-dimensional geometry and topology fits in this scheme. Let me just try to show you a few examples, so you can maybe agree or you can disagree, but let me try to show you some examples first. Okay. So what do I have in mind actually? So the first example, it's going to be the following. So this is Teichmuller theory. So what do I mean by this? Well, so to any surface, so the surfaces I want is compact oriented surfaces. I'm going to associate the Teichmuller space, T sigma. So this is a set of hyperbolic metrics on sigma with geodesic boundaries. Geodesic boundaries. Geodesic boundaries. Okay, and then further I take simply just the continuous functions on that space to be my V.
Set of matrix modulus on group or?
Yeah. So this is divided by the diffeomorphism groups of the surface, which is isotopic to that end. That's right, because this is infinite dimensional space. When I divide this out, I get a finite dimensional manifold. Thank you.
Do you require constant curvature?
Yeah, that's implied by hyperbolic metric. It means that it's constant curvature -1. So I wrote hyperbolic here. Okay. So this is the target theory. Oh, sorry, this is this function that I'm talking about. V here simply associates for every surface the continuous functions on its Teichmuller space. Okay. And then I'm sure you will agree that if I now define the function 1 inside this vector space, then that certainly satisfies all of this here. It's a totally functorial assignment, and it is Markov group invariant, of course. Now this example here seems to be utterly ridiculously trivial, but I will actually show you that this example, when we fit it into geometric recursion, actually gives you the Mirzakhani-McShane identities. Okay. But let's try to do something a little bit more fun than just taking the function 1. So let's take example 2. So example 2, the V will be the same. Okay, but now I'm going to take a different function. I'm going to go with f sigma. And at some hyperbolic structure, it's going to be the following. I sum over all curves in what I call S sigma. And what is S sigma? S sigma is the, in Thurston's notation, multi-curves on sigma. What this means is it's isotopy classes of a one-dimensional closed submanifolds of sigma, such that no component is isotopic to a boundary component of sigma. So that's the set of multicurves. Okay.
Maybe it's a topic to what?
No, neither, sorry. So one-dimensional such that no component is isotopic to a boundary component, nor a point. Thank you. I don't want them to be homotopically trivial on the surface. And then I'm going to take the product over the components in each of these, and then I'm going to apply some function to the length with respect to the hyperbolic matrix sigma of the components. So f here is just some function from the positive reals to the complex numbers, and then I will require that f has sufficiently strong decay such that this sum here makes sense. Notice that this is an infinite sum, that it is a countable set we're summing over, but it is an infinite sum, and it requires strong decay of f for this to be convergent. But if f decays, for example, if f at infinity is Schwarzschild, this sum here is well defined. It gives you a continuous function on, so f of sigma, this is in this guy over there. And of course it is Markov group invariant, because if the decay is strong enough, say f is Schwarzschild, then this sum here is absolutely convergent, and therefore the Markov group is just moving all the summates around in the sum, and therefore that doesn't change the sum. because it's absolutely convergent. So this is a very interesting class of functions on Teichmuller space that's generated this way. And it is an open problem to understand the statistics of these functions. In other words, their integration over the moduli space of curves. And I'm going to tell you a solution to this problem in the process of setting up the program. Okay. So let me go on with more examples. So this is just an example where the target theory, the V, is functions. But there are many other possibilities for this vector space. So for example, so this is example 3. Let's take V of sigma to be the two forms on Teichmuller space. And then, if I look at omega sigma simply to be the Weyl-Petersen symplectic form on Teichmuller space, then obviously that's another example that is mapping class group invariant. 4. Let's take the vector space to be the following. The smooth sections of Teichmuller space of the endomorphism bundle of Teichmuller space. Sorry, the endomorphism bundle of the tangent space to the Teichmuller space. And then in here, omega sigma will be just the complex structure that Teichmuller space has. And so I remind you, that if you look at the tangent space at some sigma, the Teichmuller space, well, that's isomorphic to H1 of the corresponding Riemann surface with coefficients in K star of that Riemann surface. And so multiplication by I is exactly what gives you the complex structure here. So this is beta's complex structure on Teichmuller space. So that fits in the scheme here. Okay? Of course, I don't need to restrict to two forms. Up here, I could have considered all forms, so that's another thing. So maybe 5, all forms. So you just take omega star of T sigma. And then of course omega sigma here is just some kind of form on Teichmuller space, which is mapping class group invariant, i.e. a form on the moduli space of curves. And so we all know that it's sort of a very interesting question to understand how do you write down explicit representatives of, say, closed forms that represents the cohomology classes of the moduli space. This is still an open problem. There are certain classes for which we know how to do this, but for the general classes, say the odd classes, we don't really know much about that in general. So we make it.
What is the convention that all, let's say, what are classes in Markovitz conjecture, homologic and modular space are obtained in such a way, or all forms are obtained in such a way?
So I haven't told you how to obtain forms yet or anything like this, but I would conjecture that geometric recursion will give you all of them.
All forms or classes?
All
forms, yeah.
representative of classes. Yeah, representative of classes.
Excuse me, I have a question.
Yeah.
What are morphisms in this category? Do we use only mapping class group, or do we have like branched coverings or something?
No, morphisms are isotopic classes of diffeomorphisms.
And how do they act on the Teichmuller space?
They act by pulling back the metrics. So if you have a diffeomorphism, you pull back the metric, and if I change the diffeomorphism by an isotopy, that's exactly the same as changing it by something in diff 0 of sigma. And so this is the isotopy. This is the diffeomorphism which are isotopic to the identity.
But we probably get something like singular, or
No.
on a branched covering, we will get complex structure.
No. So you take the space of hyperbolic metrics on a surface.
Yeah.
Do you agree that all the diffeomorphisms act on that?
Yeah, sure.
Good. Now I take the subgroup of the diffeomorphisms which are isotopic to their density and I divide them out. That is by definition Teichmuller space. And the remaining quotient group, which is diffeo divided by diffeo isotopic to their density, of course acts on.
Oh, yeah, sure.
So it's a triviality. Yeah. Good. Okay. 6. What more can we come up? Let me just remind myself of the many examples. So, I'm a little bit in doubt whether I should give the whole example. Actually, I want to definitely give the following. So, especially since one of the relevant persons is in the audience. So the next one here is the following. Let G be a Lie group and choose an invariant pairing on the Lie algebra of the Lie group. Okay. And now I define V of sigma to be, this like this way. I'm going to take smooth sections over the moduli space of flat G connections on the surface, and the bundle that I'm taking is the second wedge power of the tangent bundle to mg of sigma. Okay. So those of you who know this space very well know that this space is singular, but you then also know how to deal with this guy here. So I don't want to say more about that. If you don't know what I meant, you can ask one of the people in the audience after the talk. Because what I want to say is that omega G, omega sigma here, this is going to be the Rochely Poisson structure, which is, of course, exactly an element in that space. And of course, this is also marking up to the right. Okay. So you see, it's not restricted to just Teichmuller space. You can also do other modular spaces. And in fact, you can do something that is even more complicated than that. Let's consider the narrow symmetry. Actually, before I do that, I just want to remind you that if you look at this modular space, so I didn't write it, let me write it up. So mg sigma here, this is the modular space of flat G connections on sigma. And if you now require that the pairing is non-degenerate on Lie algebra, so that we put some constraints on which Lie group you can take, but let's assume that the pairing is non-degenerate, then what happens is the following, that you have a holonomial map, mg sigma, to conjugacy classes in G, so this is CG's conjugacy classes, and then you take pi 0 of the boundary. So in other words, you take a flat connection and you remember its holonomy around the boundaries. So you fix that. So I look at, if I inside here look at H inverse of some system of conjugacy classes attached to all the boundary components. And this guy here is the symplectic leaf of the structure. So I'm going to denote this mg sigma c. This is the symplectic leaf. So the symplectic leaves are geometrically known for this guy here. They are this form. And the nice thing about the symplectic leaves is that they are actually scalar manifolds. So that's the example I want to get to next. Is there a word? Scalar manifolds. They have many Keeler structures, not just one. They have that Teichmuller spaces parameterize as Keeler structures on them. Okay? So example what? 6, 7. Now I'm going to let V of sigma be the following. You look at smooth maps from Teichmuller space over to smooth maps, or sorry, smooth sections over M G sigma comma C of the endomorphism bundle of the tangent bundle of that guy. Okay, so I guess there's one more bracket. So that means, in other words, I'm going to think of Teichmuller space as parameterizing complex structures on these modular spaces. So this is just what's called a narrow Siemens-Shetty theorem, but in its parabolic normalization, right? So inside here, I have and there omega sigma, which is going to be I. So this is the Mirzakhani-McShane. It should be complex version. And of course I should say complex structure family, right? Because for every point in cyclical space, I get a complex structure in this modular space. So it's the usual Mirzakhani-McShane theorem. But in the case of surfaces with boundaries, and what happens is that I have to add disks to the boundaries, and then I look at parabolic connections, so connections with parabolic singularities, and in that modular space there is exactly this Mirzakhani-McShane recursion. Okay, so that's another example of this, which is more complicated, but it is true that this guy here indeed lies in the Markov class. So not only does it lie there, but in fact this guy here lies in V sigma again, and then Markov class group invariant guy. Because notice that if you just look at the Markov class group action on this modular space, then the complex structure will not be invariant under the action of the Markov class group. But the whole family of complex structures that is induced, so that's mapped from here to the space of complex structures, that is Markov class group equivariant, and therefore invariant as an action on the space. Okay, let's go on. So, next thing is I want to show that, so 8, all invariants of 3 manifolds fit in the scheme. In this scheme. How does that work? Well, what we do is the following. So remember the Singer theorem. So theorem, which is due to Singer. Maybe I should actually set up a little bit before I do that. So definition. So a cut system or compression system. So it has many names. Is a G-tuple, G-tuple of let me write it another way. Is a maximal set of maximal set of it's a long sentence. It's a maximal set of simple closed curves which are disjoint and the same as before. None of them are isotopic. None of them are isotopic to the boundary. To boundary.
When you say non-isotopic to the boundary, you mean to the multiple of the boundary or just to the boundary?
So each curve is a copy of the circle embedded, and one component of the boundary is another.
Non-intersecting circle, so it cannot.
They are non-intersecting.
Cannot read several times.
First of all, they are simple, so they cannot bind several times.
Okay.
Second of all, they are not isotopic to each other, so if I take 2 pairs and try to make an isotopy, I fail. If I take one boundary component and one of the curves and try to make them isotopic, I won't fail. And I cannot isotope any of them to a point island, just like before. And not point isotopic. And not PP isotopic. So if I were to draw a simple good example as a system, I would draw, say, maybe these 2 here on a closed surface with no boundary. Okay.
And one between the handles.
Well,
The one which is homologous to 0, but
yes,
still
sorry.
material.
Yes. And I don't really need that, but okay, I can add when I say cut system or compression system, all that I actually need on a surface of genus G is G of them. So maybe I shouldn't have said maximum, because since I spelled out all these conditions, down here I don't need to say maximal, so I don't need them. I can just take something like this. But what I do need is that when I cut the surface along these curves here, it will be a genus 0 surface with boundaries. So that's what lies in cut system or compression system.
So this, in this example, this one on board, they give dimension 3.
In this case, they are 2, because as you know, you can add one more if you like. But the thing is that I don't actually need them. I just need the number that I need is the needed thing to such that when I cut along this, the surface has genus 0 with the number of disks removed. I guess I made the mistake of now spelling all of this out, because all I want to say is heat-gun diagrams. Because heat-gun diagrams are pairs of such systems. Okay? Because they specify, all I need is just that I know how to fill in the surface with water up to 1, 2. Okay, so a heat-gun diagram, so the definition continues. Heat-gun diagram, this is a pair of compression systems. Okay, and then there is a notion of slide equivalence of compression systems.
It's not just a pair of compressions. There should be a pair of compression systems on one and the same surface.
Correct. So he got diagrams of sigma. Thank you. Let's write that short for HD of sigma. This is such systems on sigma. And indeed we will use exactly that. So slide equivalence of compression systems just means that if you have one system, I'm just going to draw an example. So here's one system. Then what you can do is the following. You can take a curve, which is an embedded curve, but it does not hit any of the other two except for its endpoints. So it's a curve that goes from one of the curves in the system to another one in the complement of all the others. Once you have such a thing, what you're allowed to do is take two parallels of this guy, like this, and then you run over, and you run around this curve. Excuse me. And then you come back like this. So this is a slide where you slide one cycle over another cycle. It's called a handle slide in this theory. So you take all of the such diagrams, and then actually what I want to do is I want to divide out by this equivalence relation. So I divide out by this equivalence relation called the slide equivalence. And you can do slides of A's over, when you have pairs, you call them A and B. So let's write them A and B. And you're allowed to slide A's over A's and B's over B's. Okay, and the main theorem is the following. Yeah, I actually just want to state it the following way, because that's what we need. Theorem, and this is due to Singer, and it says that there is, if I look at this set here of such heat diagrams on sigma, then at the moment, so yeah, if there is a boundary on the surface, I just close them off. But I mean, initially, to make life simple for myself at the moment, I'm going to assume that the boundary of sigma is empty. Okay? Then there is a map from this set here to 3 manifolds. And when I take the union over all surfaces, when I take the union over all sigma closed oriented surface, then this map is onto it. And so the way that it works is that you take this pair of compression systems, then you look at a handle body, so that, it's, basically you do the following construction, not basically, you do the following construction. You take all the A sides, these are curves on the surface. You attach a disk from the inside on the surface to all of those. Then when you look at the surface unit of the disk, and that's actually the boundary of a three-ball. So you attach that three-ball. So therefore you get a three-manifold whose boundary is the surface. You do the same thing on the B side, but then they are glued against one and the same common surface sigma, and so the resulting thing is a three-manifold. And the Singer theorem says that this is surjective. This is onto. So you can establish all three manifolds by doing this. It just simply says the three manifold has a Heegaard equal-position. Okay. And so therefore, maybe I'm giving you more details about this than I should do. But anyway. So, therefore, if I now have I from three manifolds to say some field, let's just say the complex numbers. Well, let me say some field, because I didn't specify what field I was using in the vector spaces, right? So if you have this is a three manifold invariant. Well, then you can simply just define omega sigma to be V of sigma. This is going to be take the free vector space on these Heegaard diagrams on sigma, and then you take the dual of that vector space. And so it's simply just this guy here is just this invariant. Because what you do is that if you have a Heegaard diagram, then you just associate the three manifold and apply the invariant. And then you make it linear over the field. Sorry, this should be the field. And so clearly that's something to do. So any invariant of three manifold fits in the scheme. And by the Gay-Kirby theorem that puts four manifolds on the same footing as three manifolds, because it realizes four manifolds by what's called, instead of Heegaard diagrams, Gay-Kirby diagrams, you can do exactly the same. So four manifolds also fit, four manifold invariants. So this was 8, 9, same thing for four manifolds. All four manifold invariants fit in this. Okay. And so similarly, I'm just maybe going to switch to not writing them all on the board, because then the talk will just consist on giving you examples. So this, but I can just mention some of them. So, for example, the hitching connection in the space of conformal blocks, it works the same way. Representations of the mapping class group, boundary vectors and TQFTs, universal mapping class group invariant finite type invariants, boundary vectors of handle bodies in Heegaard-Floer homology, cohomology class obtained by Gromov-Witten theory, and amplitudes in closed bosonic string theory, and so on. There are tons of examples actually where you can reformulate everything like this. Therefore, there's a strong motivation to be able to build such things in a systematic way where you consider surfaces of all types in one go. So, let me now try to do that. So now I want to focus on how do we actually somehow recursively build these. Because many of these are sort of done individually for each surface at a time, constructing some structure. But maybe we can actually build a scheme by which we can sort of very consistently try to build a theory that simply builds them all via one machinery. And that's the idea behind geometric recursion. So let me just specify the category precisely. So B here, this is my category of surfaces. So objects, this will be oriented, compact surfaces. So if you want two-dimensional, smooth manifolds. Okay, that's the objects. And the morphisms, these are isotopic classes. Actually, sorry, I want more structure. So I want to further, so so this is one aspect. Another aspect is that I want orientation on the boundary. Okay? And so if I have an orientation on the surface and I have an orientation on the boundary, I can, so let's say I have an object.
So it's not necessarily induced?
No, because what I actually now want to do is I want to split the boundary into the minus part and the plus part. And the plus part is where the induced or agrees with the given, and the minus is the opposite. And I want it exactly such that if I take pi 0 of the negative boundary and look at the natural map that is induced by including that negative boundary on the surface, this should induce an isomorphism on pi 0 of the surface. In other words, each connected component of the surface has exactly one minus boundary and all the others plus. Okay. So let me draw a little example. Maybe something like this. Here's the minus boundary, here's the plus boundary. Maybe it has some genes or something. It was a connected example. There's only one minus boundary, all the rest is plus. Okay, so that's precisely the objects that I'm going to be working on. And so I will, so that in other words, each connected component has a preferred in-boundary. Right? Now the morphisms, and morphisms are simply isotopic classes of diffeos which preserve this structure. So in other words, it just preserves the orientation on the whole surface and it preserves the orientations on the boundaries. Okay, so that category is very simple to understand, right? Very good. And now the output category. Well, that one I will give you the approximate definition in this lecture, and then in the second half, to get so far, I'll give you the exact definition. But for now, it will simply just be topological, Hausdorff complete topological vector spaces. So because I'm working in infinite dimensions, I have to be careful about precisely which vector spaces I want, and I want exactly these. Yeah, but I want them, also to be locally convex. Because I want the topology to be given by seminorms. So locally convex says that the topology is given by seminorms. Okay, very good. And so I assume that I have a functor, so given a functor v from, and so this guy was b, and this guy is going to be curly v, so functor from b to b. So this is the target theory that I was talking about. We call this a target theory because it gives you the target for where the things are going to land. So I gave you, I don't know, 9 or 10 examples of this v in before. So that we're going to assume is given. Okay. And now the idea is that we want to build invariant, Martin class group invariant guys out of this. And we're going to do this via recursion. So build omega sigma inside V of sigma via recursion. And we want to recurse in the Euler characteristic of the surface. And we're also going to restrict it in such a way that I want to only consider cases where the boundary is non-empty. Okay? So, I actually want to say more than that. I want to say that all the components should have a non-empty boundary, but I don't know how to say that right now. You know what I mean? So this is the case for connected surfaces. and the case for or component. Okay. So we have this preferred boundary, right? If I take a connected surface, I'm going to take sigma to be connected. Okay. Now what I want to do, I want to look at this surface. So this is somehow connected. You may have many other, actually I don't want to draw it like this.
But what's written last is held by the bottom line here. We have here the exit boundary.
Then, sorry, I knew that this was not necessary to say thank you. So, but I felt I had to say it, but
You
you're
could
right.
be no plus
No,
boundary.
you're absolutely right. This implies that every guy has at least one. So thank you. So what I want to do now is I want to say, let's look at the following set, that P of sigma be the set of isotopy classes of embeddings of pair of pants into sigma such that the image contain the minus boundary. And so right now I'm assuming that sigma is connected. Right? It's a connected object. So connected. This set here is of course countable, but it's certainly infinite in most cases, right? So there's sort of, let me specialize out three different kind of cases here. The first case is the following. Namely, what could happen is that this pair of pants shares two boundary components with the surface, and then has another internal one, and then there are more boundaries here, right? So that could be the case. The second case is the following. The second case kind of splits into two subcases. The second case is where the pair of pants only has one boundary component in common with the surface. And so what might happen is that one of them is the that you have a hole here, and then you have the pair of pants is here, and it splits off a connected surface. But of course, the other possibility is that it splits out a disconnected surface like this. So you have the pair of pants like this and like this. Like that. And so another thing that I should add here is that I only want to consider surfaces of negative Euler characteristics. So I also require that the Euler characteristic of sigma is strictly negative. And this I want for every connected component. Okay. All right. So now the idea is to say, well, what would be really nice, right, is that if somehow I have the vector space for the whole guy here, but I also have the vector space. If I somehow have this pair of pants, I also have the vector space for the remaining thing. And I have the vector space for the pair of pants. And I've cut along some curve which was the boundary of some pair of pants P, right? So this is the pair of pants. And so if I somehow was given a gluing map, which depends on this cut curve on P, and goes from the vector space of the pair of pants across the vector space of the complement to the vector space of the whole surface. Then what I could say is, well, if I already know what the invariant vector for this piece is, I can just stick in something for the pair of pants, and then I can map it over here, and at least I get a vector in the right space. But of course, this won't work in general, because it might very well depend on the curve that I'm cutting on. In other words, it might very well depend on this pair of pants. And one way out is simply just to solve all choices. So that's what we're going to do. That's sort of the simplest possible way of eliminating some problem with dependence. So therefore, I'm going to assume that whenever we have gamma inside sigma multicurve, in the sense of Thurston, right? Then this will give me, and I only need the case, actually. So I only need the case where gamma here is the gamma of some pair of pans. So P is in the set of pair of pans. So I only need the cases where gamma is either a single curve that encloses two boundary components, or I could have here gamma of P maybe 1 and gamma of P2, altogether being gamma of P. Gamma P1, disjoint union, gamma P2. Same thing here. So then I will require that I have, for such gammas, I have a map of V of, let me just say that I only consider the case of the pair of pans, because that's smart. I just consider these pair of pans, I have gamma inside here, so I have the pair of pans on one side, and I have the remaining of the surface I have here. So I'm going to assume that the theory gives me bilinear maps like this. Bilinear continuous maps. Okay, and then I can simply, let me make the definition on the next board here. So you see, I could have, so I need some kind of initial data. So I'm going to assume that I'm given the C of the vector space of a pair of pans. And so I'm deliberately a little bit vague about precisely which pair of pans it is, because the whole theory is going to be diffeomorphic. And so there is very few diffeomorphisms of a pair of pans, so that's easy to control. So I'm going to assume that I have a B. First of all, I'm going to assume that I have a C, which is mapping class group invariant of a pair of pans. And then I'm going to assume that I have a B, which depends on the specification. So this is going to be the B case. And these two together are going to be the C case. And you see that this guy here, so maybe this guy up here is the negative boundary, but then there is a further specification of a further guy here. This guy here, however, is totally symmetric in this. So that's why it has to be completely symmetric on the mapping class. But here I can have a guy that lies in the pair of pans B, and if I have an element of the mapping class group of a pair of pans, all that it has to do is just map 5B to the way that it moves the point on, the boundary components. So I can have two B's, because there is a specification on the pair of pans that either this is the second or the third boundary. And they just have to transform like this. So I'm assuming I have two guys like this.
Sorry, Jørgen. Do you allow your mapping class group elements to exchange boundary components?
Yeah, I do.
Including the negative one?
No. Because the isotopy is, because the diffuse has to preserve all the structure. And the mapping class group is defined to be the automorphism group of an element in the category. Okay. So now I can attempt to try to define inductively the following way. Omega sigma is going to be, first of all, it's going to be a sum over. So I can write this guy here as a disjoint union of the B cases and the C cases. Right? So therefore, I can first write it as a P in the B case of sigma, take gamma, theta here, gamma P, stick in the B, and stick in omega sigma minus P. Because what you notice is that in all cases, the Euler characteristic is one higher for this than it is for the whole surface. So therefore it's going up at least by one, or it's actually going up exactly by one each time, and therefore, since all my things have Euler characteristic negative, it will end with minus 1 at some point. So this is therefore a seemingly good induction, and certainly the deduction. And now I do the C case here, and then I take this again. Now I stick in the C here. And then I do omega sigma minus p, like this. And then just for fun, in order to match with topological recursion, I'm going to put it half here. So there are various problems with this definition, right? First of all, and the main problem is the following, is that these two sets here are infinite. So in order to do this, I have to make sense of these sums. Okay? So they have to do some analysis in order to make sense of this. Okay? Also, where does this recursion stop? Well, this recursion stops. So stop. So this was sort of recursing information, but what's the initial information? Maybe I shouldn't call it like that because we also call B and C the initial data. But it stops with, if the Euler characteristic of the surface is -1, then there are two possibilities. Either P, which is the pair of hands itself, and so then I just say, let me say that I'm also given an A inside the Markov class invariant part. So when I'm down to having the surface, the complement over there is just the pair of hands itself, I just assign A. And also for, I also want to specify T, and T here is simply just the one-hole torus. And in that case, I specify a D in the Markov class invariant part of the vector space associated to this torus. And so now I have my initial stuff, I will always end with these, and then I can just iteratively refine this if I can make sense of these sums. Okay. All right. So I think that I'm going to, yes? I think I'm going to allocate the next hour to the analysis of this. And I'm just going to assume that somehow we can set up a theory that really makes sense of these sums for now. Okay? So, so the theorem is, so maybe I formulate the theorem a little funny in a moment, but it says the following, so it's our theorem, the main theorem about this geometric recursion. So I will just say the following, under certain conditions on initial data, and the initial data is indeed A, B, C, and D, and the gluing maps by the way, I guess one thing I forgot about over here is that this here really allows us to deal with connected surfaces. But so, we're just going to do the following. So that's sort of a very simple part of it. So disjoint union, I'm not finished with the theorem yet, but I just want to remind you that, or say that if I have a disjoint union, then what I'm going to do on the V level is just assume that I have a bilinear continuous map that goes like this. And so this is a bilinear and continuous. And so if I have these maps here, of course, if I can just do things for connected surfaces, I just apply these maps here and then I get them to this. So that's not. So under certain conditions of the initial data and the gluing maps, theta gamma here, we get that this guy here, this sum here, this sum is absolutely convergent. In all seminorms. And omega sigma via this construction indeed lies in the gamma invariant part. Okay. So there is a very general machinery that allows you to make these constructions. And so let me just show you a number of examples where we already know precisely how we should select the initial data.
Excuse me.
Can you read the statement for us?
Yeah.
Why
The
do-
statement says that under certain conditions on the initial data, which is in combination with the gluing data. So there are some conditions that combines the initial data and the gluing maps. We get that this sum here is absolutely convergent in all sim norms, and it gives you a well-defined omega sigma, which lies in the mapping class group invariant part of this vector space.
Why do we take 1/2 of the second term?
I can't hear you.
Why do we take 1/2 of the second term?
Why do I put it 1/2? This you will see a little later. It's because I wanted to match the topological recursion. Okay, so you will see. What I wanted to do, you will see.
But like invariants won't automatically drop if you.
Yes, invariance will never mix these terms with these terms. Because they're topologically distinct, right? So an element, a diffeomorphism, can never throw a situation here to a situation here. So you could put A and B here, and it will still be a true theorem. So this half you can just ignore, because you could just define, it's a bilinear map, you would put the half in on C, right? It's just because I wanted to check with topological recursion. Okay, so let me show you some examples of this. So when I'm going to take this target theory we started with, namely functions on Teichmuller space, I hope I can find it somewhere here. Yeah, so it must be here somewhere. So V of sigma in this example, so example V of sigma, this is going to be continuous functions on Teichmuller space. So the first question is, what is Teichmuller space with a pair of bands? Well, these are hyperbolic surfaces, right? And so they have boundaries, and the boundaries are geodesics. So if you specify what the lengths of the three boundary components are, you have specified the metric completely. So therefore, this is just R plus to the 3. So when I have to give you initial data A, B, and C, I just have to give you 3 functions of 3 variables, right? So A is going to be very simple. A is just going to be a function 1. Okay. And then here is B and C. So B is going to be a function of L1 and L2, and then little l, and that's because this is the case where I have 2 guys at the boundary and then an internal guy, so I call this variable L, this is L1 and this is L2. So the function is the following, 1 minus 1 over L1, and then Ln of cos hyperbolic to L2 half, plus cos hyperbolic to L1 plus L half, divided by cos hyperbolic to L2 half, plus cos hyperbolic to L1 minus L half. Like this. And then C, I have L1, and then I have L and L prime. So now the picture looks like here is L1, then it goes into the surface, and I have L here, and then I have L prime here. And so because I'm not distinguishing these two, the function better be symmetric in L and L prime. And so the function is 1 over L1, Ln of x of L1 half plus x of L plus L prime half, and then x of minus L1 half plus x also of the sum. So if you take A, B, and C to be this, and you take P of sigma to be the sum over all curves on, so I can just actually write it as S of the torus. So remember that I'm considering the one-hole torus, and so you just consider all possible other curves on the torus, which are not trivial homotomically, and which is not homotopic to the boundary. And so when you cut along that, you will get a pair of bands. And indeed, we will just use C So it would just be C of L, so L is out here, and this length of this guy is there. So L, L, L of that gamma. Sorry. L of gamma, L of gamma. So that's the function D. Okay? Now, so the theorem is the following. And so this is really repeated. So you define the formula I'm rubbing out right now is the formula you have to use, apply to these guys here, and then what you will get is a function on Teichmuller space. So the theorem says that this function is simply the function 1 for all surfaces. And so it's simply just repeated applications of the Mirzakhani-McShane identity to see that this happens like this. Okay, so it's a kind of, partition of unity, you can say, in relation to geometric recursion that we have discovered this way. But it's just, in this case, it's just a reformulation of the Mirzakhani-McShane identity. Okay, now, so...
And the gluing map,
Yes, so I haven't defined what the gluing map was. That's right. So thank you. Let me do that. Sorry, I forgot to tell you what typography is. I can do that. So what is this gluing map? So gamma P here is V of P cross V of sigma minus P to V of sigma. Well, what I do is I take Teichmuller space of paired bands, and then I consider Teichmuller space of the sigma minus P. So what this means is that it's a hyperbolic metric on P, and it's a hyperbolic metric on the complement of P. And so what you see is that there's actually a map from here, from Teichmuller space of the whole surface, by simply just mapping, just restricting the hyperbolic metric to 2 parts. And it's very easy to understand what the image is, because the image is exactly the subset here, where the boundaries that are in common between the two have the same length. And so if I have a function here, and I have a function here, I just restrict them to the image, and I multiply them. So that's all that's happening with the gluing map. That's the gluing map. So I don't want to write it down, so it's clear, right? And with a disjoint union morphism over there, well, the Teichmuller space of the disjoint union of 2 surfaces is just the cross product of the 2 Teichmuller spaces, because it's a metric on one and a metric on the other. And so the gluing map is just pull back to the cross product and multiply. Okay, good. Can I go for, say, 10 minutes more?
Yeah.
Oh, okay, fantastic. All right, so now let's do the more interesting guy. Let's do the guy with the summing of all multicurves. So we just recall for you that f of some sigma here, depending on sigma, this was the sum over all multicurves on the surface, and then we took the product of the function applied to the components of the multicurve, right? You took pi 0 of the multicurve, that gives you a number of embedded circles. You take the length in this metric. Sorry, why did I write that? I should write the gamma twiddle, and then sigma gamma twiddle, like this. So notice that I really allow the empty multicurve. So this guy here starts with 1 plus all the things with 1 component, and then plus all the things with 2 components, and so on. So it's actually rather easy to check that if you look at the disjoint union of 2 surfaces, then of course this is just the product of the 2. Of course, pull back to each of them, but I don't want to write the bookends. So this is multiplicative on the disjoint union. Okay, so that's already a good sign. And now what I want to do is give you the initial data that gives you these functions. So it's interesting to see, you see, if you look at a function like this, you might say, let's try to simply just take a surface, like this, and let's cut it down the middle. And then you have some holes on one side, and you have some genus on one side, and have some holes on the other, and genus, and so on. And so, this is going really well as long as you keep the curves on one side or the other. But if you start looking at what happens if the curves go across the cut lobes, this really makes hell break loose at the cut lobes. And that's why this guy here doesn't have a very simple gluing formula when you cut along the curve. And so it doesn't really satisfy the usual sort of axioms that such a guy would if you were doing usual quantum field theory thinking. That you get a contribution from this side, you get a contribution from this side, and then you have some kind of integration over intermediate states in the middle. It's maybe possible to do that, but it's very, very complicated. Because the matching condition has to be right with the angles and I don't know what and so on, so it's not very easy to write this. I don't think anybody has done that in this case. However, in this case here, where we are doing this kind of different recursion, where we're summing over all possible ways of extracting pair pairs, what you can do is that you can simply somehow rearrange all the terms in such a way that you never see this phenomenon. You never sum over terms where the curves give the pair pairs. You only sum over either things that are in the complement. So you always sum over terms where the pair pairs are in the complement of what you have. So this doesn't really tell you what the proof is, but that's the main idea of the proof. Namely that if you start with the following initial data, L1, L2, L, and this is B, so there's Mirzakhani-McShane initial data, that's the ABCD over there. Is it still over there? Yes, no, yes. And then you add to this plus F of L. So it's very simple perturbation that actually will give you this very complicated function here. F here, F perturbation of C. You just take C of L, and then L prime of L. And then you've got to produce something that's symmetric, so you just take P of L, L, L prime, F of L, plus, and then you symmetrize P of L, L prime, comma L, and then F of L prime. Like this. And then you have to take a grad term as well, F of L times F of L prime. And AF is still exactly the same, and DT of sigma is 1 plus summing over the curves in the multi-curves of T, which is just one component, regard across to the pair of pairs, and then F of L of, in respect to sigma of L. So these initial data will give you that guy. So theorem. Okay. So yeah, I guess it's going a little slower than all together. I wanted it to. Let me just maybe state one of the main important theorems. So what you can now do, so what, you know, what was the sort of big thing about Mirzakhani's generalization of McShane's work? Well, it was really that she got this beautiful recursions on the volumes of the moduli spaces. And that really generalizes nicely. So theorem, what you can do is you can define Vf to be the integral over the moduli space MGN with length L1 up to Ln. And what you now do is you take F sigma times omega sigma. So this here is just the Liouville volume form. Okay? And this is just the function multiplied onto it. So what we're talking about here are averages. So some people, you know, in physics we would write it like this. So these are expectation values of these functions when you integrate over moduli space. And so the statement is that these guys here are given by topological recursion. And so if I didn't have the half in there, I couldn't make this statement now. But now I can make it totally clean. So in other words, these guys here are very easy to compute using topological recursion. And so, the reason why they satisfy topological recursion is because this guy satisfies geometric recursion. As I said over there. And so the proof goes via that. And so, what this means is that you can either say it in two ways. One way is to say that they satisfy specific, this just becomes a function, this here just becomes a function L1 up to Ln. And so it satisfies very explicit integration equations or recursion relations where you just integrate on one or two variables in the lengths. Or you can say it as I wrote it, that if you take these functions, which are functions of L, and if you do the Laplace inverse transform in every Li, you get something that now depends on, say, Zi's instead. And those guys are given by topological recursion. And so this is a general phenomenon. I think I'll just state that theorem by saying, namely, if you have anything that you already know is given by topological recursion, you can take the initial data for that topological recursion, then you can produce by some explicit means initial data for geometric recursion. You can run that and get functions on Teichmuller space. When you do that, multiply those functions until you will volume form and integrate over modular space, you will get back the amplitudes that topological recursion gives you. So all instances of topological recursion, there are many things that are already known to be given by topological recursion, like all matrix models are solved by topological recursion, for example. You can then turn that into spitting out functions such that when you integrate over modular space, you get back the amplitudes that the topological recursion is computing. So the story is much longer, but let's maybe stop here and then we can talk about what more you would like to do.
So whether D is D.
Sorry?
D.
Right. Thank you. DF.
So, can you do the theory with different ABCD?
Yes, many different ABCDs, right? So, I mean, if you want, I can show you one for forms. Everything that I have done in terms of examples so far, after I've
No, but even here, meaning that, so here this pair with some conditions and then this is different. So okay, we'll have different cuts of remote surfaces which give you again geometric recursion.
I'm not sure I understand the question properly.
So let's say that instead of, so I guess you have to have an elliptic curve, but can we have two elliptic curves? Two D's instead of just one.
Well, you can change the D completely independent of A, B, and C. So D you could decide to be something completely different than this if you wanted to, but then the resultant cost would be different.
Yeah, yeah. Okay. So there are many
ABCDs.
Okay. And each of them give you theories which are kind of independent.
Yes, they give you new things, but then you ask interesting questions, namely, which equivalence relation is there on quadruples ABCD that gives you the same function in total? And I don't know what the answer to that is. And second question would be, what equivalences is there on ABCD such that they give you the same expectation values? I don't know the answer to that either. But I can say that it sort of has to do with topological recursion, because you can also start with any initial data for geometric recursion and produce initial data for topological recursion. And so there we know that if you go, that it's only the initial data for topological recursion, of course, that determines these guys by this theorem. So there it's kind of clear. But because there's quite a lot known, but not, as far as I know, complete answer to when two different initial data for topological recursion give you the same answer. But quite a few things are known already there. Certain actions, like there is an action of the Leaving-Tart rule or something like this, that doesn't change the amplitude. But not for genus 0, but for higher genus it changes in a very specified way and so on. I'm not really an expert on that, but I know that there's lots of things known about what can you do that doesn't change or that changes the topological recursion answer in a very specific way.
Other questions? Well, let's thank Jørgen. So we're keeping 15 minutes in the second part of the talk.
What I could talk about now, before I do that, I want to show you another example that is not about functions, but about forms. And so, let me go to that. So actually, it's quite simple to obtain the Poisson structure by simply taking the usual expression with the Poisson structure and for surfaces with boundaries, and just multiplying the A, B, and C on it for the pair pairs, and then doing nothing but just taking the Poisson structure for D. And so if you do that, and run the geometric recursion, then you will actually find that what's built by geometric recursion is your Poisson structure. So that fits in the scheme. But now I'd like to show you something else that sort of... So it's very explicit what I just said, right? I mean, it's completely straightforward to do this, but I just want to show you an example with forms on Teichmuller space, so also higher degree forms. Sorry, it's very far away in this note. Here we go. Yeah. So, and so what you have to do is you have to build something that is multiplicative, basically, when you do disjoint union. So you cannot just take the form itself, you have to exponentially form. But so, and also I must say that I should work with slightly different Teichmuller spaces. So I'm going to introduce a new Teichmuller space. And this Teichmuller space is actually for surfaces where you have a mark point on each of the boundary components. And so let me not specify what this Teichmuller space is. I mean, I can just say it in words. That what you have is that you look at hyperbolic metrics just as I did before. But now what you do is you, when you define the equivalence on hyperbolic metrics, you only look at diffeomorphisms which preserves this point here. And all the isotopies also preserve the points on the boundary. And the effect that this has is that they build R bundles over the usual Teichmuller space because there is a certain amount that you can twist around each of the boundary components. And this cannot be undone because of the mark point. So that's very simple. And then if I take the Dean twists that are along the boundaries, because all of a sudden they're non-trivial in the theory when I have mark points on the boundary, I can divide those out, and then these R bundles become U1 bundles. And that's the reason why that the Teichmuller space for a pair of pairs becomes R plus, as we had before, but then cross U1 to the 3. So that's actually this sort of special Teichmuller space when you have mark points on the boundary. Okay? So before we just had R plus to the 3, as we had functions over here.
Is that for pairs?
That's for pair pairs, that's right. Yes. And in general what will happen is that this guy here, because I've divided by this Dean twist along the boundary, will map to this guy here, and, sorry, sigma, and the final is U1 to the number of boundary components. So just write precisely to the boundary. So it's some circle bundle over the usual type. But this is very important when we want to do this recursion with forms. And now the gluing maps will be more involved because when you glue, the thing is that Teichmuller space, you know, as I said before, it was just a simple inclusion of the Teichmuller space of the cut thing into the Teichmuller space of the cut pieces. But now it becomes a little bit more complicated, and there is actually a U1 bundle over the cut locus. Okay? But that's really good because then we can push forward our forms by integrating over fibers. And this is actually what allows the whole thing to work. And so the initial data that you have to take is A should be X of, so let the coordinates be Li and theta are in here, so this should just be summing going to be the B of Mirzakhani-McShane over there. So now I've chosen to name the coordinates L1, L2, L3, like this, always. And then you have X of taking the two that are from the boundary and making them like this. So the same thing as before in A, but then you have to multiply on by wedge of just this guy here. And this has to do with, if you just have this one form here wedged on, you will get exactly the right push forward map. And then C is the C of Mirzakhani-McShane. And then you have just one copy of the X, so X of E theta 1 with the L1. And then you have the two other boundary components contribute the same one form as in B, like this. And then finally D is simply just X of, well, D theta with the L plus D phi with the L. And so I have to tell you what these coordinates is. So if you have a one-hole torus like this, say I choose one cut curve here, and it has length L, and when you reglue the metric back in, it has a twist which is phi, and then at the boundary here you also have L and theta that twist at the boundary. And so it's just like this. And so then the theorem is that you always get that the amplitudes are X of omega while Peterson. X of omega while Peterson. You know, 1 plus omega squared, and so on. Divided by 2. Only 2/3 divided by 3 factorial. So this is a way to actually get the whole exponential series for the Ray-Peterson symplectic form on Teichmuller space. But you have to go to this other Teichmuller space where you have points on the boundary. Okay. Now, maybe I will tell you a bit about the analytic side of the story. So why does these infinite sum actually make sense and work? Okay. And so here we have developed sort of a general notion that generalizes hyperbolic geometry. So certainly hyperbolic geometry and things to do with Teichmuller space gives you an example, but it's not really necessary to only stick to that point of view. You can do something much more general. So let me show you how that goes. I just have to find it again. And that could take a while. Sorry. Notice also I want to remark one thing, and that is that this theory here didn't ask for any relations between A, B, C, and D, right? It's completely free theory. And there is a version of this theory here that's different. Namely, you see, this thing here had a preferred in-boundary and all the rest. So the whole thing is symmetric in the outs, but not when you commute in and out. But if you want to have a theory that really can commute in and out also, we have a version of that, but then you start having relations between A, B, C, D. And it's actually very interesting because in the work of Kontsevich and Zeugelmann, they also have these A, B, C, D tensors. And the relations that they have in order for them to define what's called a quantum area structure, or what they call a quantum area structure, those relations we have lifted to this setting here, and they become relations which involve actions of Martin classical elements. So it's kind of an interesting thing to see how that goes. Now, let me just try to find this in my notes. Yeah. So, I told you before that V here, this was the category of Hausdorff. Complete, locally compact topological vector spaces. And I'm going to work over C, actually. But this is actually not quite true. And so it is certainly true that, for example, if we take the theory of Teichmuller space, and we take the continuous functions, or smooth forms, or whatever, it will be such a vector space, no doubt about it. But it basically has to do with the following thing, that when you look at hyperbolic metrics, and you degenerate the surface, some of the lengths can become, of course, arbitrarily small. And this will somehow mean that we lose control over norm estimates. And so therefore what we have sort of figured out is an analog of looking in Teichmuller space at what's called system sets. So system sets are the subset of Teichmuller space such that the shortest geodesic is bigger than epsilon. That's the epsilon system set. And basically what we can do in that example is to prove convergence on each of the system sets at the same time. And then we don't get uniform estimates on all of the semi-norms for the whole Teichmuller space. We cannot prove convergence in that topology, but we can prove convergence in sort of when we filter the whole theory over system sets. And so that we have abstracted out to the notion that I am going to give you now. So I'm going to first introduce a category C, so define C. And this is going to be a specific category, and then a target theory will take values in C. So what are elements in C? So objects are the following. They are directed sets, J. Think of those as the positive real numbers in the case of Teichmuller theory, where epsilon runs in the system, runs in that. But abstractly, they're just directed sets, and inverse limits. Of VI, and then semi-norms. So these VIs, they are all Hausdorff complete locally, they're all from V. So these guys here all lie in objects from V. And then I specify the semi-norms because I have to talk about some properties about those. And so the semi-norms for each of these vector spaces is indexed by some set I'm calling AI. And then this is a directed set where I is running through J. So it's a directed system, an inverse limit system. Why do I say inverse limit? I don't mean that inverse, I mean the directed system. Directed system, because the inverse limit comes in a second. So it's an inverse system of such vector spaces and an object V of this guy here, which actually is the inverse limit of I and J of these VIs. So think of V as the set of continuous functions in Teichmuller space, and think of that as being the inverse limit of the system where you have the Teichmuller spaces, subspaces of Teichmuller space with systems bigger than or equal to epsilon, and you take the union of all of those, and so therefore you can filter the space by just looking at inclusions of these when you have epsilon 1 over epsilon 2. And second of all, I want to define the following thing. I define the following norms, or semi-norms. They're only semi-norms, and they could possibly be infinite, these values. So I take, let's see, I, and then I take all the semi-norms for given I, and then I take supremum over O alpha. And of course, in general, when you do that for such a convex vector space, locally convex vector space, you're not going to always get something finite. Because when you take supremum over all semi-norms, this could be infinite. That's fine, I just allow this to be of infinite value. And then I define V prime to be the V's in the limit space, such that all of these guys are finite. For all I and J. Okay, so the category that I want to have is a directed set and a directed system of Hausdorff complete locally convex topological vector spaces, such that I can always do, this category V has limits, so I can take this limit here, and then I can consider these seminorms, and I can look at the subspace for which all these seminorms are finite. No problem. Okay. And I don't want to specify what a morphism is, but you can imagine what a morphism is. A morphism is a map, from, what you do is you say for all, maybe I should say it because it's kind of complicated, because of these directed sets. And also that will be important when we study how this guy here, how we use this to prove that these norms are actually working, and give you some finite. So I'll just say that, if morphism, so that's the phi from such a V1 to V2, where we denote this collection with this like this. Maybe I put a bar under to signify that we really have this whole collection. So like this. So what this means is that I have phi ij from Vi1 to Vj2. But I only have this for all I in J. And then I have a map. So, it's understood in the following way where H is some map from your J1 to J2. So this is a directed map. It's an order preserving map. And under this order preserving map, what holds is that for all I get that for all J less than H of I have this. Okay, so it's a linear map which induces, a linear map on the limits that takes these subsets to each other. Okay. So then I sort of explicitly said what this means. Okay.
Do you consider continuous maps?
Yes, sorry, when I meant map in the category of V. So in this is, yeah, so I let
You
you
cannot say what, when you introduce the category, what are the morphisms?
No. I meant in this category.
Continuous.
Yeah. So these are all continuous. Sorry. And these are all continuous with respect to, of course, the seminorm. Okay. So now, I want to define to you what a target theory is. Definition, so a C-valued target theory is a function from B, and B stands for Bordisms, in case somebody wondered about B, to C. Okay, so let's call the function something. Let's see, maybe I call it E, to not confuse it with any other stuff. So E of sigma, in other words, spits out this directed set, right, of all of these topological vector spaces with their seminorms, like this, where I is running through some J sigma. Okay, so together with the following. And here there's something that seems strength with length functions. Abstract length functions. And where are they going from? So the Li, first of all, what are these length functions indexed by? The length functions are going to be indexed by exactly the same indexing set as the seminorms are indexed by. So J, A of I. And what's the reason for that? Well, the reason for that is simply just that, okay, you take an epsilon, a real number bigger than 0, you look at the subset of Teichmuller space with that system, and then you take a compact subset inside there. That's what indexes the seminorms in that case. So I is the positive real line. You pick an epsilon, which is 9 here, and then an alpha here is a compact subset. And then when you have Teichmuller theory, you can just take, say, the supremum over all metrics in this compact subset, and then the length of the curve. And that gives you a length function. And so that's why, in the general theory, we have let exactly the indexing set for length functions be exactly the same as the set that indexes the seminorms on these vector spaces. So, therefore, I ask that the target theory gives me length functions which can measure length on these simple closed curves on the surface or multi-curves, right? And it goes into, well, I don't want to formulate it for the general field, I just say the complex numbers minus 0. So it's not allowed to hit 0. It's not allowed to give 0 length to any curve. Because if it does that, I can't control what happens with these infinite sums. Because these guys here are going to control these infinite sums. Okay, but now they have to satisfy a stack of actions. And they're not so complicated because you can guess them from hyperbolic geometry. So basically we just sort of somehow look at the hyperbolic geometry example and then we just take out the properties exactly that we need for the length functions. And so the first one is polynomial growth. And so the polynomial growth action says the following. You define ni alpha, so indexed by the same as the seminorms, of the surface L. So these are the curves, multi-curves, whose length is no more than L. Okay, so first of all, if you do this for Teichmuller theory, right, so you look at the set of curves that within a compact subset in Teichmuller space has length no more than L, you will get a finite set. So that's the first assumption. This has to be finite for all I in J sigma and all alpha in A I. Second of all, what does happens for Teichmuller theory? Well, this guy grows in polynomially in size, right? It grows like a polynomial at most. So therefore, we just assume there exists mi, or this functorially defined for the surface, comma di, also functorially defined for the surface, in the positive reals, such that if you look at the supremum over all alphas in I, AI, and this is of course of sigma, should have been no sigma here. So that means now you're looking over a system set, and not just over a compact, but over the whole system set, by taking supremum over all alphas. And take the size of this set here. And so what Mirzakhani has proved is that there are these mi's of sigma L to the di of sigma, if you were talking hyperbolic geometry. So we just now assume that these length functions exactly has this polynomial growth property. Okay? Very good. And now, then it also has to have a lower bound, and this is exactly the system condition. The lower bound action. And this says that for all I in K of sigma, there exists an epsilon I bigger than 0, such that if I look at the infimum of Li alpha of gamma, so the lengths where alpha and gamma is running through the indexing set for the norms, and I run through all curves. So in other words, I'm looking for systole over some systole set, right? Of course, this is bigger than epsilon. So now we're just saying there exists an epsilon I for each of the i's such that this happens. Okay. And then there is the final one, which is called the small pair pansection. And so the small pair pansection says the following. If you look at an I from ij, then there exists a qi bigger than 0, such that the following holds. So that for all alpha in ai of sigma, and any boundary component b of the plus surface. That's where the B, the other leg of the parapath is going to go. If you look at the following sizes, put them over here. It simply just says that there are finitely many parapents where the legs inside the surface, the combined length of that is smaller than the length in the boundary.
So,
Yeah.
will they repeat it once again?
Yeah, let me write this over. Well, maybe I can say it right away. What I'm going to write here is, you know, you look at a pair of pants embedded in a given hyperbolic surface. There's only a finite amount of curves that are smaller than the length of the boundary, because the lengths are accumulating towards infinity. And now we just want it uniformly over the system sets. And in hyperbolic surface, that's clear because you're just saying the following. Because there is a lower bound for the shortest curve, clearly there's a lower bound for the end of the pair. So, okay. So it says that I take the size of the set of pair bands in the surface, which is of B type, and then I ask that the length, with respect to I and alpha here, of gamma, that's smaller than the length of the two outer boundaries. B1 plus L I alpha of B. And this is smaller than or equal to QI. So this number is bounded. Second of all, if I look at P that is of C type, the same thing happens, but now I have only one outer boundary. So the sum of alpha of gamma plus the length of gamma prime, so these are the two inner parts of that, is less than the length of boundary of it. And again, I require that to be less than or equal to QI. So this is the precise actions for the target theory. And I'm telling you that Teichmuller space satisfies this. It's simply just an abstraction from what we use from Teichmuller theory. And now I can formulate a precise theorem, namely this theorem that I'm going to have to remove the first thing here over here. Because I also have to tell you what is the precise condition on the initial data. Right? Remember that there was this thing that initial data has to satisfy some analytic estimate in relation to the gluing mass. Because that's the only place where the decay in this sum can come from. So let me just state that. I can find it here. Yeah. So actually before I write the theorem, I have to write a definition about it. So we have a notion where we say something admissible. What does it mean that initial data is admissible? Admissible initial data is the following. Namely, you take any sigma which is an object of B, and you take a P which lies in the set of pair pants, sigma, and let's take the one for B. Then it says that for all I, j, in J of the pair pants cross J of the surface minus the pair pants, and for all K in the glued surface, such that K is less than or equal to the gluing map, I mean this H-ordered map that you have from this category, from the cross product over to the thing, the object for the glued surface, and for all alpha in A of K of sigma, you have, I guess it's terrible if this is the right one, Ij, you have constants that depends on Ij and K of the surface which are bigger than 0, and you have that there exists an Sk which is bigger than dk of sigma plus 1, such that following inequality goes. So if you take the gluing map for that curve corresponding to the pair of pants, and you take the ijkth entry of it, and you stick in the guy you have for the pair of pants, and you stick in any vector on the other side, and you measure the alpha norm of this, and that is bounded above by a constant ijk that depends on the surface times the norm of J. And so you see that V, this is for all V that lies in E prime of the whole surface, because I have to be able to talk about these, or at least it's only relevant for those that lie in this here. Plus, and then you take the following thing, L K alpha of gamma minus LK alpha B1 minus LK alpha B, all of that, and then you take this bracket plus, and the bracket plus just means if the real number inside this bracket is negative, you write 0, if it's positive, you write whatever it is. And then you take that,
It's
to the
called
y.
Heaviside function.
What's that?
Heaviside function.
Heaviside function, it's the positive Heaviside function. Thank you. That's right, and then you lift it to minus sk. So this gluing map is bounded by exactly this. And there is a similar statement for C. Okay. And now I can formulate the theorem, and I can give you the main idea of the theorem, or the proof of the theorem. So the theorem precisely says that, so if we have, if E is the target theory, and A, B, C, D is admissible initial data, then GR is well defined the sum is absolute conversion in each seminorm and moreover omega sigma will actually lie in this E prime of sigma. So it will have finite these norms here that I wrote before for all of them. And this is very important because we really need to show that those norms are finite in order to continue the recursion, because those are the ones that control the next step. So if we couldn't prove that it was in this prime space where all of these supremum norms here, over seminorms are finite, we wouldn't be able to continue. Okay, and so, yeah, I don't think I want to write out what the sum is, right? I mean, you know what the recursion sum is, I wrote it in the first lecture. So maybe that was the one point that I sort of fairly detailed explained what that sum was. Okay, so what's sort of the main crux of the proof here? Well, the thing is that so you see, what we really have to do is we have to do the following. We basically have to take a sum through a mapping class group orbit of the simple closed curves. Right, so let's consider the B case. So remember, the B case is just something where the pair of pants looks like this. So these two are boundaries of the surface also, and this is internal. So what I'm now going to do is I'm going to take a mapping class group orbit of these, because that's what I have to sum through. Okay, and then I consider the gluing for those, so let me call that gamma still. So gamma is running through this mapping class group orbit. I'm taking B and inserting it in the first place for B, and then I take the rest of the surface and I take omega for that. And I'm assuming that I already have these by induction. And so now I have to contend with this sum here. And of course, it's fine if I can take the relevant seminorm of this. So if I take the alpha norm and I restrict this to looking at the ijk part, So remember, I have, you know, the two vector spaces. The objects where this is lying, or the places where this is lying, is say indexed by I. The places where this is lying indexed by j, and the output is indexed by k. So I take the ijk norm of that, or ijk map on these set of directed sets, and then I take the alphas semi-norm. So take this. But now I can simply just, it's really, really very simple when we have formulated like this. Now you just take, so what I see here is exactly what I have in the sum over there. So now I just substitute for what I have here. So now I just write that this is certainly less than or equal to the same sum. And then I have the stuff that I see on that side, so that is these constants, which doesn't depend on the orbit, right? So they can go outside. Mij, ij, k of sigma, and also I see vi, vj. So that goes outside, and the only thing that remains inside is this 1 plus, and then this horrible long thing, I alpha, gamma, minus the two lengths of the boundaries that are outside B. This is gamma, and this is B1, and this is B. B1 minus I alpha of B. So all of that plus Heaviside, positive Heaviside function. Now, what I'm going to do is to say, well, this could be problematic, because this returns 0 if this is negative. But then we look, when are this negative? This is negative when the combined length of the boundary is bigger than the internal length. But there's only finitely many of those by the axiom that I worked out, which is called the small pants axiom. So finitely many terms of this sum I can take outside completely. And then I am left with that the Heaviside function just returns the functions as it is. By the way, I forgot to the minus sk, like that. And now I see just some numbers, right? And those numbers, how fast are they growing? They are growing like a polynomial in L. Because that's what my polynomial axiom says, right? The polynomial growth axiom says this quantity here grows most like a polynomial. But then I can just say, okay, well then let's look at that polynomial growth, because that just exactly becomes the zeta function, right? Just becomes the Riemann zeta function evaluated for that particular L inside, the maximum length. So therefore, all of this is simply bounded by this zeta function at minus at sk. And so if you choose sk to be 1 faster than the polynomial growth, because this was the polynomial growth. So already, the moment sk is bigger than the polynomial growth, the thing over there is finite, but it's also universally bounded if we take one more. So therefore, this gadget here just becomes less than some constant that depends on, I don't know how much, but it certainly depends on that, of sigma, and then this norm vj, and then some other constant, I don't know, n, and it only depends on the orbit too. So therefore, and of course it depends on k, because this guy depends on k. But I don't care, it can depend on ijk any way it wants. But now I've shown that when I sum the norms, the semi-norms, that's convergent. But then this is exactly what it means that the sum is absolutely convergent for every semi-norm. And so therefore this works, and then because this thing on the other side here only depends on ij and k, and the orbit, and I only finite many orbits, and I only missed finitely many terms, I see actually that it has finite semi-norms. When I take the supremum for each given k, take supremum over alpha, this is finite because it doesn't depend on alpha the right hand side for that. And so that's actually the proof. And so we can run recursion and you know, get the theorem as it says.
So is it the scheme of this Mirzakhani-McShane
Only
similar to this? Or?
no, not at all. She works with hyperbolic geometry. She does various things. I mean, the way that she proves, she just proves this identity. I mean, she's not making this setup. That's our idea, the setup here, and all of this generalization. But what she does is she says she wants to look at a smart way of measuring pair pants inside a hyperbolic surface. And so what she says is, I'm going to take a boundary component, and I'm going to take a geodesic that is shot off orthogonally to the boundary. And then she says, it can do one of three things. It can come back to the same boundary again, or it can, four things I guess, or it can go to another boundary component, or it can go out and hit itself, or it can run dense on the surface. And what she proves is that the ones that run dense on the surface is of measure 0 on the circle. And then the remaining things are exactly those different types of pair pants. And so therefore she can write the integration of the measure, the uniform measure on the boundary, so that just keeps the length of the boundary, as a sum over pair pants, and then she figures out how much mass is the C case and the B case. And that's how she derives her formula.
It wasn't she who proved that this is measure 0, in fact.
It probably wasn't her, right? Or was it? It was the older theorem, right? Yeah, but she computed what the contributions for the two other things was. That's right. Yeah. Right. So, so that's really what she did. And this is, in that sense, a generalized McShane, because McShane had done it for, I think, the one-hole torus or something like this. So his was a special case of this, but she did the general surface case. And also this idea of doing this integration. It was hers, but well, if you want, I could say, I could continue for a while, but I could, for example, say how this is related to Max and Jens' other work, and if you like to this.
I mean, if you can review that, and people can read, but actually.
So, you know.
Sorry for the egoistic.
No, I fully understand, but I think I probably killed you completely. But so this A, B, C, D also features very prominently in Max and Jens' work, right?
So what are they?
What's that?
What are they in the case?
In their case, they are really tensors. And so it's because you have to think about the vector spaces that are relevant in this case is basically sort of when you Fourier decompose maps from the circle. So this is the way that you somehow get from, when you're doing topological recursion, when you're really talking about mirromorphic objects on a Riemann surface with some punctures and so on. What you do is you put a little circle around each puncture and you Fourier decompose everything there. And then you just look at that as a linear space, and then you define various tensors in that space. And then they become these A, B, C, Ds that we have here, but the interpretation is totally different in their work and in what we do. Because we have them interpreted as some kind of elements in these funny categories I've defined, which, for example, could be functions or forms or metrics or complex structure or whatever you want. But in their case, it's really real value tensors. I mean, if you want, I can give you 10 minutes on the basics of what they do.
Yeah.
Okay. Just have to find it. But then it's only, let me say, to be fair, it's only one half of what they do. Because the other half is to do with D modules and so on. That I can, of course, not cover in 10 minutes. But I can cover the really basic stuff that they do and show you the tensors.
Who we are talking about?
Maxim Kontsevich and Jens Ellegaard. So, we're going to do the following. We're going to take V. So V is not the V that I had before. So V is a C vector space. And now we don't worry about topology or anything. It could either be finite dimensional, in which case topology is irrelevant, or if it is infinite dimensional, we just do everything formally in a basis. Okay. And so now what we're going to do is we're going to say, WHV, this is going to be the Weyl algebra generated by T star V, which is of course V direct sum V dual, over the ring of power series in H bar. And so all that matters, really sort of with the, but this is the Weyl algebra, so with the relation that if you take a vector and you commute it with a covector, this is simply just H and then take the covector and apply to the vector. So this is the usual bracket in the Weyl algebra. And that of course lies in C power series H. So that's again central. And so, definition by Conservitz and Zeta-functions. So, Conservitz and Zeta-functions. It says, so this is quantum area structure. And it's called quantum area structure because it's a kind of generalization of, if you take the area curve and apply topological recursion to that, you get an example of what I'm going to write out under some transformation. But a quantum area structure, this is a linear map from V to the Weyl algebra on V, such that there exists the basis xi, I running in I, basis of V, such that Li, so that just L applied to xi, L applied to xi of course. This is exactly the following operator. Differentiation with respect to xi, h bar, minus, and then summing a plus b in the interval, and then there is a half, and then there is a. Here's the first tensor, a, I, a, b, x, a, x, b, minus h bar, and then here's the second tensor, b, I, a, b, x, a, b, x, b, minus, and then h squared over 2, and here's the third tensor, ci, a, b, and then dx, a, dx, b, minus h bar, d, I. So, where a, b, and c, and d are scalars, a, I, a, b are the scalars, so they are tensors. And so you see that a, b, c has 3 indices. And if you want to compare to what I was doing before, these 3 indices run on the different boundary components on the paired pairs. And then D has 1 index corresponding to the fact that it's a 1-1 torus. And so it's a linear map such that it has this basis. And here comes the important condition, namely these Li generate a Lie algebra. So the image of V here is a Lie algebra inside the Weyl algebra. So, such that the commutator of Li with Lj is summing f a, I, j, L, a running in I. And so I think that you should think of this as generating, these operators generating a D model. And the whole sort of important thing, the main theorem of conservatism and Zeta-functions is the following. So, what I could do is I could also write it, but I don't want to. But you can just very quickly write down what does it mean that these Li's close. So these are scalars. So you can very quickly write down what it means that these close to a Lie algebra, right? They become just linear equations on A, B, C, D. They're sort of complicated quadratic equations. And those are the quadratic equations I'm saying we have been able to lift to our language so that they become various sums over mapping classes is 0. But here they're just linear relations, quadratic linear relations on A, B, C, D in order to satisfy the question like this. And one of the simplest things you can prove immediately is that F here is B anti-symmetrized in these two indices here. So if you anti-symmetrize B in those two indices, you get the F's.
So this is how the connection with integrable systems shows. So
Yes, exactly. So this, because if you imagine this is infinite dimensional, you have an integral system. And so F here is simply just geosymmetrized in those two indices, A and I. So although they look differently, A, B, and I, to me, they are, if you think of them as the same footing, not like I before and alpha. Okay. And so here's the main theorem of these two guys, is that there exists a unique partition function, F, which is inside h bar to the -1 sim v star with coefficients power series in h bar. And so you can write this guy out as F as summing g bigger than or equal to 0 and n bigger than or equal to 1. You take h bar to the g minus 1, divide by n factorial, and then you write f gn, where f gn lies in sim n of v star, such that, it's a pity I can't fit it in, maybe I can. Namely, if you take Li, which is the differential operator, and you apply it to x of f, you get 0. And the initial conditions are, let me write them up here, f01, 0f02. Notice that's the non-stable ones that I eliminated also. These are 0. And the other initial data is, I write it here, f03 is equal to a, and f11 equal to d. So that's the initial data, and you see A and D plays exactly the same role as I had it. A is the starting thing for the pants, which is genus 0, 3 holes. And D is the starting thing for genus 1 and 1 hole. But so the interest...
So basically, in the same way, they have some basic integrable systems from which they kind of seem to do the whole thing, and that's the way the recursion goes.
Yeah, but their formalism is not equivalent to ours. This is a special, their formalism is a special case of ours. Namely, if we take as target theory functions that only depends on the boundary length of a hyperbolic surface, so no dependence of any interior coordinates in Teichmuller space, then we get a theory that's exactly equivalent to their theory. So it's a special, very special case, their theory. Yeah. Then of course what you can do is you can write down a recursion. So given, these equations here can of course be rewritten in terms of recursion on these FGNs. And the recursions on these FGNs you would recognize as the algebraic analog for our equation of the recursion. But now you will interpret things just over these indices. So if you want, I can write this out. I mean, it's the obvious thing you would do. You see that, so you just write the FGNs of the indices I1 up to In, and then you just look at what recursion relations will they have to satisfy in order for the LIs to kill the exponential of F. And you will come out with exactly the formula for topological recursion, or geometric recursion. But now, of course, in this very special case where you just have these indices that live on the boundary. So the conservative Zuckerman picture is a special case, a very special case of ours, but not vice versa. But it has its ABCD formalism, and when we were developing this geometric recursion, Max shared some notes about this with me, and I realized that this was really the language that was much smarter to use instead of this, spectral curves and so on that are used in topological recursion. And so I combined it with the pre-existing ideas we had about how to topologize this, and then we ended up with the formalism we have. I have presented for you. So I don't think it's the time of the day where you want to see line after line after line of relations that this devolves to. But one thing that I want to challenge you with is the following. Look at this expression here. This is free energy, right? So think of this as the position for a total position function with sum of all G and N.
So
So
this, is it some Gromov-Witten expression?
Well, I mean, because this formalism here is actually equivalent to topological recursion in the infinite setting, or rather, let's say it this way. When you take V to be the infinite, an infinite dimensional vector space with a countable basis, then this setting here becomes totally equivalent to topological recursion. So consider subdomain quantum area structures for the case where V has a countable basis is equivalent to topological recursion. And then we already know that Gromov-Witten invariance for, say, toric-Calabi-Yau satisfies the topological recursion. So we know that Gromov-Witten invariance satisfies this recursion scheme here for the toric-Calabi-Yau. It's a conjecture that they always satisfy this for all Calabi-Yau methods, by seeing or by Inard and following their proof of the remodeling conjecture by Mourinho, right? Because Clement and so on. So the attribution of that conjecture is, I think they will all claim it if it's correct. And it's fairly so, I would say. If it's not, they will probably run away. But people are expecting, I suppose, that Gromov-Witten invariance will satisfy this. But I just wanted to, the comment was the following. So, here's the position function. We take the free energy by taking log, right? And so the interesting question is, can something like this be true in our theory? Because in our theory, all these guys here live in different vector spaces. Because when you fix G and N, they live in these vector spaces. That depends on the genus and the number of outcomes. For example, if we do the Teichmuller theory, these will be functions on a surface of genus G with N boundary components, right? So it's a function on that Teichmuller space. So here you're summing over all genus and all N, so it doesn't really a priori make sense in our formula to create this object. But maybe they're all inside this universal Teichmuller space that contains all the Teichmuller spaces. I don't know. Maybe you have to interpret this way, then you can make sense of this equation. I don't know. But Sergei is talking about this universal Teichmuller